Hi, I'm Connor, and today I'll be presenting from Khalil's Nonlinear Systems, specifically Chapter 8, which covers Advanced Stability Analysis. So starting off, I'll just do a little outline here. We'll start with an introduction, going into the sections from the chapter, starting from center manifold theorem and going to stability of periodic systems. So a little reason why I wanted to do this presentation, I thought the Nonlinear Systems book was very readable. It's nice, informative, and it provides a sort of intuitive basis for the proofs. One thing to note was it was a little hard to get a good quality scan, so for most of the theorems I've rewritten them out nice and clear for you. So starting off with center manifold theorem, some background before we get to the actual theorems. We have our nonlinear autonomous system as we're used to seeing, x dot equals f of x, where f is some continuously differentiable function and d is a domain containing the origin x equals 0, which we'll suppose is an equilibrium point. After computing the Jacobian, we can linearize the system and represent it as you can see here on the left, where this f tilde is twice continuously differentiable and has these conditions. Now we're interested in the case where linearization fails to inform us about the stability. So we have these conditions here, k eigenvalues with 0 real parts. We can find a similarity transform such that we can obtain this block diagonal matrix where the blocks have these properties so that we can analyze the stability. With a change of variables, we get this new system here, 8.2, 8.3, and for our purposes, we can think of a k-dimensional manifold in Rn as the solution to the equation eta x equals 0, eta being a map from Rn to Rn minus k and is sufficiently smooth. This manifold is said to be an invariant manifold for the system 8.1 if eta x of 0 equals 0 implies that eta x of t for all time is equivalent to 0, where 0 to t1 is the interval of existence for our solution x. Now back to the main idea. If this z equals h of y is an invariant manifold for the system 8.2, 8.3, and h is sufficiently smooth, then it is called a center manifold if h of 0 equals 0 and partial h by partial y of 0 equals 0. So now we arrive at the theorems. I put the equations at the top, so they're still available. Starting with theorem 8.1, if g1 and g2 are twice continuously differentiable and satisfy our conditions 8.4, all eigenvalues of a1 have 0 real parts and all eigenvalues of a2 have negative real parts, then there exists a constant delta and a continuously differentiable function h of y defined for all norm of y less than delta, such that z h of y is a center manifold. We can see this theorem says that there exists a center manifold for a sufficiently small y. If the initial state of the system lies in the center manifold, then the solution will lie in the manifold for all t. That is, z of t is equivalent to h y of t. In this case, the motion of the system in the center manifold is described by the kth order differential equation here, which is referred to as the reduced system. In the case where z of 0 is not equal to h y of 0, then the difference, z minus h, represents the deviation of the trajectory from the center manifold at any time t. Now this is particularly useful, especially with our theorem 8.2, under the assumptions of theorem 8.1, if the origin y of 0 of the reduced system is asymptotically stable or respectively unstable, then the origin of the full system is also asymptotically stable, respectively unstable. What this means is we can determine the stability of the full system based on this smaller reduced system. At a glance, we can see the theorem 8.1 works because changing coordinates does not change stability properties, and we follow a typical Lyapunov proof with comparison functions. Here we have two corollaries to go along with our theorems. It's important to note the existence of the Lyapunov function cannot be inferred from a converse Lyapunov theorem. The converse Lyapunov theorem for stability we saw earlier in the course guarantees the existence of a Lyapunov function that's time dependent, but in general this function cannot be made independent of t. We can choose the function to be continuously differentiable in its arguments, but it cannot be guaranteed that the partial derivatives will be uniformly bound in some neighborhood of the origin for all time. To actually use theorem 8.2, we need to find the center manifold z equals h of y. The function h is the solution to the partial differential equation here with these boundary conditions. However, this equation in general cannot be solved exactly. If it could be solved exactly, then that would imply we know the center manifold, and thus we would know solutions to our system already. However, we can approximate a solution arbitrarily closely with the Taylor series in Y. So theorem 8.3 gives us insight on how we can still use theorem 8.2. If we can find an approximation of the center manifold with some leftover difference on the order p, then our reduced system will have leftovers to the order p plus 1. which is a good result, and we can determine stability based on this. So this gives us a procedure for determining an approximation for the center manifold, and then thus determining stability behavior of our system based on this reduced system and the center manifold. Next, on to chapter 8.2, covers region of attraction. To put it simply, we have a lemma if x0 is an asymptotically stable equilibrium point for x dot equals f of t x, then its region of attraction Ra is an open connected invariant set. Moreover, the boundary of Ra is formed by its trajectories, suggesting one way to determine region of attraction is to characterize trajectories that lie on the boundary of our region of attraction. So here we have an example, the van der Pol oscillator in reverse time. We can see that the region of attraction is bounded by the limit cycle, and all trajectories inside this region of attraction approach the origin. Many examples also involve finding the largest balls about the origin where our Lyapunov function have negative definite derivatives in time. Now on to section 8.3, which covers invariance-like theorems, starting off with lemma 8.2, or Barbalat's lemma, which we saw in the course. We have theorem 8.4. Given these conditions, we can determine that all solutions of x dot equals f of tx with x at t0 within some ball such that this function w2 is less than rho are bounded and satisfy Wx of t tends to 0 as t tends to infinity. Moreover, if all of the assumptions hold globally and w1 is radially unbounded, the statement is true for all x t0 in Rn. The limit implies that the trajectory x of t approaches a set E where w of x equals 0, and the positive limit set of x is a subset of this region. This is a weaker conclusion than the invariance principles for autonomous systems that we found earlier in the course, where we know the positive limit is an invariant set. Some non-autonomous systems have some sort of invariance property, such as periodic systems and asymptotically autonomous systems. But in general, the positive limit sets are not invariant. It is possible to conclude uniform asymptotic stability, though, based on the next theorem, if we show not only v dot is less than 0, but v decreases over an interval t to t plus delta. So theorem 8.5 does exactly that. And we show that if v is decreasing on some interval t to t plus delta, for some delta greater than 0, then the origin is uniformly asymptotically stable. And if all of our assumptions hold globally, and this w1 is radially unbounded, then the origin is globally uniformly asymptotically stable. If we can also find w1 of x is greater than or equal to k1 norm of x to the c, and w2 is less than some k2 norm x to the c for k1, k2, and c greater than 0, then the origin is exponentially stable. The proof for this is quite similar to what we saw in the class as well, where we set up v less than some class KL function. Finally, we have stability of periodic systems, which just comes with a few definitions so we can determine what it means for a periodic system to be stable. Starting off, definition 8.1, the closed invariant set M of x dot equals f of x is 1, stable if for each epsilon greater than 0, there's a delta greater than 0, such that x of 0 inside a delta neighborhood implies x of t is within the epsilon neighborhood for all of time greater than 0. And 2 is asymptotically stable if it is stable and delta can be chosen such that x at 0 is within this delta neighborhood implies that the limit as t tends to infinity of the distance between x of t's trajectory and the set M tends to 0. This definition actually reduces to our definition of stability that we determined earlier in our course when M is an equilibrium point. We can also see if there's a function v which is 0 on M and positive in some neighborhood of M excluding M, and if the derivative is negative semi-definite, we have stability as in our examples we've seen in the course. Further, if v dot is negative in the neighborhood excluding M, then M is asymptotically stable. Next, a little bit of setup. Let u of t be a non-trivial periodic solution to the autonomous system x dot equals f of x with a period t, and let gamma be the closed orbit defined by gamma equals the set of x in Rn such that x equals u of t for the interval t between 0 and the period. The periodic orbit of gamma is the image of u of t in the state space. It is an invariant set whose stability properties are defined by the definition 8.1. Lastly, definition 8.2, a non-trivial solution of u of t of x dot equals f of x is 1, orbitally stable if the closed orbit gamma generated by u is stable, and 2, asymptotically orbitally stable if the closed orbit gamma generated by u of t is asymptotically stable. Thanks for listening to my presentation. I had a good time learning the material from this chapter, and I had a good time learning material from the course. So thanks for teaching, and hope you enjoyed.